So guys, in our previous video, we have understood about the mathematical intuition behind linear regression and multiple linear regression. Now we are going to understand some of the performance metrics that is used to determine whether the model is good or not for a specific problem statement. And the metrics that will basically be used is something called as R squared and adjusted R squared. Now let us understand what exactly R squared is and what is adjusted R square and what is the exact difference between both of them. Now first of all, let's go ahead and understand about R square, and R square is basically given by the formula which looks something like this. So this is R squared is equal to 1 minus sum of square residual. I'll talk about what is this residual and all, and this is sum of square total. Okay, so here a simple definition that you can probably see is that R squared is nothing but 1 minus SS residual, that is sum of squared residual, divided by sum of squared total. Okay. Now let's understand what is this sum of squared residual. Suppose if I say this is my problem statement, let's say this is my x-axis, y-axis. Okay. And I have some of the data points which looks like this. Okay. Which looks like this. Okay, I'm just drawing some data points over here. Our main aim is that we need to find out the best fit line. So if we are trying to find out the best fit line with respect to this orange points, these are my true output, right? So I specifically say all these points belongs to y of I, right? Y of I are basically my true outputs, right? Now similarly, with respect to this particular point, the predicted point is nothing but this part, right? So this I can basically say it is y of I hat, right? Y of I hat. Y of I hat are my predicted points, right? So this is my predicted point, 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 this is my predicted point. So I'm just drawing all my predicted point. Now, whenever I try to find out the difference between them, then in short, I am basically saying that as this is basically my residual, okay? Residual or error. So if I probably try to find out this particular distance, this particular distance, this distance, this distance, this distance, and this distance, this is basically the residual. Okay. Now understand the definition over here. I am basically writing 1 minus sum of square residual. So I can basically write this as with this notation, that is summation of y of I minus y of I hat whole square. Right. So in short, what I'm doing, I'm basically trying to find out the difference between y of I and y of I hat. Okay, and I'm doing all the summation of all this particular residual or error. I can also say this as errors. Okay, now this will be divided by sum of square total. Now what is this sum of square total? Now with respect to this particular point, I hope everybody found out, okay, this is my best fit line. But with respect to the y-axis and with respect to all these y points, if I try to calculate the average, okay, so if I try to calculate the average, then you may probably be seeing that y of I average will come with respect to this specific point. Okay, or let's say I'm just trying to calculate all the y of I points. I'm just taking all the y of I points and I'm just calculating the average. Now, in with respect to this kind of distribution, let's assume that my y of I is basically getting passed over here. This y of I hat, I will say. Okay, so this basically indicates this is nothing but average of the true points, that is y of I. Okay, average of all the y of I. Now this sum of square total basically means, if I really want to give it in a mathematical notation, this is nothing but summation of y of I minus y of I hat whole square. So this basically means that we are trying to find out the difference between the true point and this specific point, which is basically indicated by y of I hat. Y of I hat is nothing but it is the average point. Okay, so from here to here I'll calculate the difference, then from here to here I'll calculate the difference. Similarly, here to here I'll calculate the difference, here to here I'll calculate the difference, here to here I'll calculate the difference, here to here and here to here. Okay, so this orange line that you see, this is basically the mean of all the y of I points. Okay, so this basically will be giving my R squared value. Okay, now here you can clearly see that obviously just by simple understanding, right, you can definitely see that y of I minus y of I hat whole square, this residual, this difference of the residual, because my best fit line passes through almost near to all the true points, right? So this particular difference will be smaller number when compared to this particular difference, right? Because this is with respect to the average, this specific line, and obviously the distance will be quite big. So here I can definitely write something like this. I will write that it is y minus, let's consider this is a small number when compared to the denominator, right? So the denominator will be a bigger number, right? Small number divided by bigger number. So now when we do this kind of division, obviously we are going to get a smaller number itself, right? So let's consider if this numerator is a smaller number and denominator is a bigger number. Obviously when we try to find out the division of these two, obviously we are going to get a smaller number. So 1 minus smaller number will be, very much near to 1 itself, right? It will be approximately near to 1. So let's consider that, suppose if I'm getting 0.70, right? So this basically indicates that I am actually having 70% accuracy, right? Suppose if I get this specific difference is somewhere around 0.85, this basically indicates that I'm getting a 85% accuracy. Suppose if I say it is 0.90, I'm actually getting a 90% accuracy, right? So with the help of R squared, we are able to find out how our model is performing, right? And more this value, understand, more this value, it is towards 1, right? More accurate my model is. More accurate my model is. More accurate my model is. My linear regression model is. Okay. But there is something called as overfitting, okay, which we will probably discuss as we go ahead. We are going to discuss about overfitting and underfitting. Just in some time, we'll discuss about it, how we need to identify whether the model is basically getting overfitted or not. For that, we really need to understand what is trained data, test data, validation data. Just give me some time. We'll discuss about that as we go ahead. Now, let's go ahead and understand about the second performance matrix, which is called as adjusted R square. Now, with respect to adjusted R square, okay, how it is basically different, that also we are going to discuss with respect to the R square. So here I'm just going to write my adjusted R square. Okay, R square. Now guys, if I consider this specific example, let's say I have in my data set, okay, I have in my data set one feature which is called as, let's say one of the feature is like size of the house. Okay, size of the house. Suppose this is my data set. I need to really predict what is the price of the house. Okay. So I need to predict this specific thing. Let's say I have one of the feature which is called as size of the house. So I'm definitely going to write price over here. Now suppose if I have size of the house and the price of the house, as we know that as the size of the house increases, my price is also going to increase. So there is a direct correlation between size of the house and price of the house, and this is usually happens in any state or any region that you are probably staying, right? The size of the house as it is increases, the price also increases. So and similarly, when the size of the house decreases, the price also decreases. So here we can definitely find something called as a positive correlation, right? Positive correlation, a good positive correlation. So when we have in this particular case a good positive correlation, then what happens? My R squared value probably increases, right? Let's say this value basically increases. Now let's say in this particular case, when I'm using these two features, and let's say that I have actually computed my R squared. My R squared value that was coming was somewhere around 75%. Let's say 75% is nothing but 0.75 with the help of this same formula. Okay, let's say with the help of this same formula that we have used over here, we got 0.75. Now what happened is that, let's say I included one more feature. After the size of the house, I said number of bedrooms. Now you know that as the number of bedrooms increases, right, the price is also going to increase. So from this, I can definitely say as my number of bedroom, and this is just a domain knowledge, right? When the number of bedroom increases, my price also is going to increase. So here also, I can definitely see something called as positive correlation, right? So when I'm actually seeing this positive correlation, now if I go and probably find out my R squared value again, after I create my model and probably plot or get my best fit line and then apply this entire formula, okay, I am definitely going to see some increase. Let's say here, I'm just assuming that I got 80% accuracy. So this is nothing but 0.80. This is also perfectly fine. Now, similarly, when I try to add one more feature, with let's say this particular feature is location, and we know that with respect to location also, it is more positively correlated with respect to price. Okay, these two are more positively correlated. So there are again chances that my R squared value will definitely increase. Okay, my R square value will become 85%. Let's say, I'm just assuming it has now increased to 85%. Now, let's say that, okay, this many features I have, okay, this many perfect, so many independent features I have, and this is my all my independent features, and this is my dependent feature, right? Now, let's say that I have added one more feature. Now, this specific feature basically says that which gender are going to stay in this house. Okay, whether they're, I'm just adding one feature. Okay, that does not make any sense. Okay, and obviously, you know that if I consider gender with price, obviously, just by common sense, there will be no correlation with respect to price, right? Anyhow, no correlation. Whoever gender stays over there, obviously, price is not going to get affected, right? But if we add this particular feature, which is not at all correlated with price, and again, if we try to probably solve this problem, which again in the future I'll be showing you in with the help of practical example, if I try to see the R squared value, even though these two variables, this input feature and this output feature are not at all correlated, then also since we are applying this particular R squared formula, there will be chances that this particular value will still increase, but it will not increase by a bigger value. So here you can see that I'm actually getting somewhere around 87%. Let's say, okay, I'm just assuming 2 more percent it got increased, because the formula works in that specific way of R squared is that as more number of features you keep on adding, somehow the R squared value is going to increase. Okay, and these all things I'll show you in practical also, guys. So let's say this become 0.87. But now there is some kind of problem. Even though this particular feature is not at all correlated with price, here you can definitely see that my R squared value is increasing. Okay, I did not prove it practically yet, because I'll do the practical and show you with respect to this particular problem statement also, right? So in this case, the R squared, you can see that even though this and this feature are not at all correlated, still it is basically increasing, right? So this is the problem with respect to R squared, right? So this is the problem with respect to R squared. Problem of R square. Even though you don't have a feature that is directly correlated with the output feature, then also this particular value increases, since the formula is in that specific way. We are just trying to find out the difference between residual and difference between the mean of which we basically say it as SS of total. Now, in order to prevent this, we basically use something called as adjusted R square. Now, in adjusted R square, what it does is that it penalizes with respect to every feature that are not correlated with the output feature. Okay, so this is what amazing thing basically happens with the adjusted R square. Now, in order to define the adjusted R square, we basically use a very simple formula. So I am basically using R square, or the adjusted R square. So let me write down the formula over here. And again, you do not know how the formula is getting derived, guys. That is not at all important, but instead we should directly use this kind of performance metrics. So it is nothing but 1 minus R square, and I'll talk about each and every term, multiplied by n minus 1 divided by n minus p minus 1. Okay, now let me talk about what is this n, what is this p and all, right? So n is nothing but, we basically say number of data points. Okay, number of data points. So that basically means in our data set how many data points are actually there. Okay, and p basically indicates number of independent features. Number of independent features that we are using. Now, guys, whatever formula that we have written over here with respect to the adjusted R square, one amazing thing that you will be finding in this, and later on when we do the practical implementation, that thing will be clearly visible to you. So let me just note it down over here, and in the later stages in the practical part, I will try to show it to you. Now, n basically means number of data points, p basically means number of independent feature. Let's say initially my p value is something like 2. So this basically indicates that, let's say my number of independent features are 2. In this case, let's say my R square is 90%. I'm just assuming, I'm just giving you a hypothetical scenario, right? If my R square value is 90, then if I try to apply the same formula with respect to R square adjusted, then here you'll be seeing that I will be getting less than this particular R square value. So here, let's say I'm getting 86%. Okay. Now, as soon as I increase p value, then obviously you know that we have seen that the R square value will increase. Okay, let's say the R square value has got 92%. And let's say that Additional one feature that we have added, the independent feature, is not at all correlated. Okay, not at all correlated, or it does not have a direct impact on that specific output feature. At that point of time, you will be seeing that the R square adjusted value will get reduced. It will be somewhere around 82, 83. It will be less than the previous one, that is less than the 86%. Here I'm just giving you a hypothetical number. Okay, this kind of scenarios you will be able to see with the help of adjusted R square. Suppose if the additional independent feature that I have added is directly proportional to the output feature, one thing that you will be able to find out that it will increase and it will be greater than this 86%. If it is not at all correlated, then it is going to decrease. This is the assumptions I'm making it right now. Okay, later on when I try to show you with respect to the practical, you will be able to find it out. I guess like you may be thinking, okay, Krish, how did this specific thing happen? Just understand, guys, when I am probably increasing the p value over here with respect to the denominator, and when I start multiplying or divide with this specific value, this kind of relationship will automatically be formed. So whatever problem that we had in the R square will basically get solved with the adjusted R square. Okay, so for right now, just make this hypothetical note that I've actually made in front of you. Later on, I'll try to show you with the help of practicals also. So this was about the performance metrics. Most common performance metrics that we use is something called as R squared and adjusted R square. And this same thing I will show you in the practical. And when I'm showing you in the practical, there are also some kind of assumptions that we made. Like over here, I spoken about correlation, right? And here also I showed you about like how R square adjusted is basically getting decreased. This is the formula that gets applied instead of this. So because of that, that specific value is getting decreased. Okay. So let's continue the video, and in the next session, we will discuss about more practical implementation. Thank you.